In this lecture, we look at the mass and energy analysis of control volumes. This is covered in chapter 5 of the textbook. The key topics that we are going to learn in this unit are conservation of mass, conservation of energy, or the first law of thermodynamics, and we will apply this to do mass and energy balance for thermal systems. Now, in previous units, we saw what is called as a closed system, one in which there is no mass transfer across the boundaries, but there is heat and work transfer permitted. Work transfer is permitted. Opposite to closed system, one can think of an open system where both mass and energy in the form of heat and work may flow in and out of the system. If you think of a closed system, how would you apply a mass balance for a closed system? By definition, there is no flow across the boundaries. There is no flow of mass across the boundaries. So the mass of the system is a constant. That would be the statement of mass balance for a closed system, whereas for an open system that has inlets, there may be several inlets, and outlets, there may be again several outlets. So let's say we have inlet, inlet, outlet, outlet. The system has inflows and outflows. Now, what is the principle of conservation of mass? It's just simply saying if we have a mass of a system is constant. Now, in this case, we don't take a system approach, rather we take the approach of a control volume, wherein this volume is the control volume. Control volume is simply the volume of interest to the particular problem or analysis. Now, how do you apply the conservation of mass for a control volume? So I'll just draw the control volume without showing the system or without showing the physical device. So I have this control volume. The boundary is called the control surface. Control surface. I'll call it CS. And across the boundaries or across the control surface, there may be inflows and outflows. Okay. So how do you do a very simple balance of mass coming in and leaving the system? So if you have mass coming in, whatever comes in minus whatever leaves must be equal to the mass that accumulates over a period of time. That is, the rate at which mass flows in minus the rate at which mass flows out should be equal to the rate of change of mass within the system. Now, this is a very simple statement of mass conservation. If you had only one inlet and one outlet. Now, this is a simple equation relating the inflow and outflow when there is only one inlet and one outlet. I can generalize this statement and write the sum of all the inflows minus the sum of all the outflow of mass should be equal to the rate of change of mass within the control volume. It's a simple statement that just says now I can generalize that statement and write the sum of all the inflows minus the sum of all the outflows should be equal to the rate of change of mass within the control volume. Now m dot is mass flow rate. M dot is mass flow rate, and we can think of any system. If it is a steady flow system, then we can say that the rate of change of mass within the control volume is 0, which leads us to a mass balance of the form sum of all the inflows is equal to sum of all the outflows. Mass flow rate may be computed as the density times the average velocity times the area of cross section. Like for example, if we have a flow or a system that looks like a Y tube, it is a Y-shaped tube. We have this to be section 1, section 2 and section 3. Let's say we have two inflows, one through section 1 where the average velocity is V1 and one through section 2 where the average velocity is V2, and let's say the density is rho 1 here and rho 2 here. We need to compute what would be the mass flow rate at section 3, as well as when we say the area is A3 and the velocity is V3. So let's apply mass balance for this very simple situation. We have sum of all the inlets, mi dot going to be mi dot 1 plus mi dot 2. So this is rho 1 V1 times A1 plus rho 2 V2 times A2. The outflows sigma mo dot is simply mo3, which is rho 3 V3 times A3. Now what is our mass balance for a steady flow system? Mi dot summation equals summation mo dot for a steady flow system. Now in this course we'll only see steady flows. So as far as this course is concerned, the working equation for mass balance is this equation, sigma mi dot equals sigma mo dot. Now what is the sigma mi dot and sigma mo dot? We can substitute for that and write rho 1 V1 bar times A1 plus rho 2 V2 bar times A2 should be equal to rho 3 V3 bar times A3. Now I told you that let's say all these quantities are specified. If we were to compute, let's say, what is the effective density at section 3, we need to know either the velocity and area, or if we know the density and the velocity, we can compute area, or if we know the density and the area, we can compute the velocity. So this equation may be inverted to write m3 dot equals rho 1 v1 a1 plus rho 2 v2 a2. So this is mass balance for a steady flow system. Since in thermodynamics, specific volume is used because it is also a state variable, we want to state the equations of mass balance in terms of the specific volume instead of density. So what is our mass balance? Sigma mi dot equals sigma mo dot, or sigma rho at the inlet times the velocity at the inlet times the area at the inlet over all the inlets in that system equals summation of rho at the outlet times the velocity at the outlet times the area at the outlet over all the outlets of that system. Now we do know that specific volume is inverse of density, which we can use now to write the equation as Vi Ai divided by nu I over all the inlets equals Vo velocity at the outlet times Ao divided by nu O over all the outlets of the system. As an example, I'm going to solve problem 5-13 from the book. And let me state briefly the facts of the problem. And this is about a pump. The inlet to the pump is water at 100 kilopascal and 15 degrees Celsius. The pump exhausts the water at 900 kilopascal and we do know that the inlet to the pump is a 1 centimeter diameter pipe. It's a 1 centimeter diameter pipe, and the exit is through a 1.5 centimeter diameter pipe. Diameter pipe. Now what we need to determine is the velocity of water at the inlet and outlet when the mass flow rate through the pump is 0.5 kilograms per second. So we do know that the mass flow rate is given to be 0.5 kilogram per second, and we need to determine the velocity of the water at the inlet and the velocity of the water at the outlet. That's what we need to calculate. So how do you apply mass balance for a system? The inlet flow rate equals the outlet flow rate. We just have one inlet and one outlet for this pump. Okay, so rho I Vi Ai equals rho O Vo Ao. We can write this in terms of the specific volume. Vi Ai over nu I equals Vo Ao over nu O. The pressure, temperature at the inlet and the pressure at the outlet are given for us to look up nu I and nu O for water at 100 kPa, 15 degrees Celsius and 900 kPa, and there is no information given about the temperature of the water at the outlet. But since this is a pump, it's reasonable to assume that the temperature doesn't change too much. We can assume the same temperature and make the assumption that the compression by the pump is adiabatic. And you do know that adiabatic means the heat change is 0. So using these pressure and temperature values, you need to look up the properties of water at 100 kilopascal and 900 kilopascal. at both at 900 kPa. If you look at table A5, you get that the saturation temperature Tsat is 99.61 degrees Celsius, and at 900 kPa the saturation temperature is 175.35 degrees Celsius. Both these temperatures are more than 15 degrees Celsius, or in other words, the temperature of the water in the pump is less than the saturation temperature at that pressure. Temperature of water is less than the saturation temperature at that pressure. What would this make? This would make the water that of compressed liquid, and I have told you before, a good approximation of the properties of a compressed liquid can be obtained by using the properties of the saturated liquid at the specified pressure. So by that assumption, the specific volume at 100 kPa and 15 degrees Celsius is approximately equal to the specific volume of the saturated liquid, which is 0.001043 meter cube per kilogram. So we have the specific volume at the inlet to be equal to 0.001043. Similarly, the specific volume at the outlet, which is 900 kilopascal and 15 degrees Celsius, is approximately equal to the specific volume of the saturated liquid at that temperature, which is 0.001121 meter cube per kilogram. So with these numbers, I have VI AI over nu I equals VO AO over nu O. I do know AI, which is pi by 4 times 1 centimeter squared, and AO is pi by 4 times 1 centimeter or 1.5 centimeter squared. And I also know that the mass flow rate itself is given to be 0.5 kilograms per second. So what do we know here? We know the area or cross-section area of the inlet and outlet. We just determined the specific volumes from the tables. We know the mass flow rate. So by equating each of the inlet and outlet flow rate to 0.5 kilogram per second, you may solve for VI and VO. Okay. VO. The exact numerical values are left for you as an exercise, and we will discuss that during lecture.